So welcome everybody. I'm super pleased to introduce our guest speaker today, Dawn Nafus, and I've just learned I've been mispronouncing her name for several years now, which is super embarrassing, because I've been following her research very excitedly over the last few years. Dawn is a senior research scientist at Interlabs, and she is an anthropologist by training. And it's always super fascinating to me how anthropologists contribute to technology planning and thinking big picture and thinking about, well, what's happening in 5 and 10 years from now. And one of the topics she's currently working on is the question of carbon responsive computing. And I'm really thrilled that she's here today. I asked her to spend about 30 minutes to 40 minutes on an actual presentation, and that should give us plenty of time for Q&A. Hakan is on this call here, so if you have a question, just type it in the chat. If there's anything that's absolutely urgent throughout the talk, type it in the chat, and Hakan will monitor this. And at the end of the talk, you can either unmute yourself or use the chat for questions. And without further ado, welcome, Dawn. It's great to have you. Hi.
Well, nice to meet you all, at least virtually. As Antonia has said, my name is Dawn. I'm a social anthropologist over at Intel. And the work I'm going to talk about today is the results of a review paper that recently came out with one of our senior engineers and a fellow science and technology studies scholar. So I'm going to do the paper has a lot of meaty technical detail in it because I'm the anthropologist on the paper. I'm going to sort of give a much more socio-technical view, a kind of a big, broad overview of what I see happening as changes in computing infrastructure, changes in energy infrastructure, and how those come together. So I'm not, so I guess one thing to say is, Hakan, if people do have sort of clarification questions, acronyms, I'm not telling you what they mean, things of that nature, please do interrupt me because I don't want to sort of bang on about something that's not necessarily familiar to everybody, right? This is supposed to be a kind of a broad and accessible talk, right? That's kind of my goal here, right? So, right. So what I'm going to look at is, so carbon responsive computing is an approach to decarbonizing the computing infrastructure that we have. And so the way I'm going to do it is first I'll talk about sort of the size and scope of the carbon footprint problem within tech. Sometimes I call them ICTs, which is how they're called in the literature sometimes, depending on which literature you're dealing with. Then I'll look at some of the signs of carbon responsive computing emerging in the computing infrastructure, right? What changes in the computing infrastructure start to look like. Then I'll briefly touch on changes, fairly straightforward changes in the energy infrastructure, which you will immediately recognize, meaning we have renewables now, so that changes the picture. And then I'll talk about how those sort of come together and really make for interesting sites for innovation, new kinds of opportunities to really do some cool stuff. With those opportunities come a whole bunch of social questions. And so in the last part, I'll elaborate on what those are. And I kind of have a little small joke here about how not to see like a high modernist machine. This is a reference to a contemporary classic in my field, which is seeing like a state, which is how sort of large bureaucratic organizations sort of erase any phenomenon that's not convenient to them. And so, of course, in my view, that's not limited to states. That's sort of any large entity. And so, if we're building technologies from the point of view of utter disregard for the social lives of various people, right, that starts to become a problem. And so, that's my attempt to kind of steer things, make sure that the right questions are being asked in the right ways socially. Okay. So. Tech, it turns out, has a massive electricity consumption. And it's kind of remarkable, right? If you think about it, when you put your computer, when you plug in your laptop at home, electricity is really not the thing that you're thinking about, because it's not, it's really not going to affect your bill, right? The heating will, your refrigerator will, right? Those types of things. But, your laptop, not so much. It turns out that when you aggregate across lots of different aspects of the computing system, right, where the consumer device, the stuff you own, is actually a very small piece of a very, very large picture, right? As sort of packets get sent through the network off to a data center, right? There's a whole bunch of electricity that just gets drawn in making the equipment at all. And this is pretty sizable, right? So there's, I put in for comparison things like, the annual energy consumption of large industrialized countries like Germany, which actually is a very small slice of global consumer electronics. And then you get into the big stuff, right? So this is really quite significant. And of course, because of that, concern is really growing, right? So from time to time, you see in the tech press and the popular press and academia, particularly lots of worry about data centers because they are the largest site of electricity draw. Global internet traffic, the IEA tells us, surged over 40% in the COVID pandemic as we sort of came home, went online, right? So no sign of slowing down. And this translates into greenhouse gas emissions. So one of the things we did in the review articles, we looked at, we found a review of reviews, a review of peer-reviewed estimates for greenhouse gas emissions from the tech industry. And it's usually, they hover between just south of 2% to just south of 3% of global emissions. That is around the same estimates you get for the aviation industry, right? So we think about the aviation industry as, this site where we really do need to curtail greenhouse gas emissions. We absolutely do. But in a sense, this remains invisible because we tend to think about, the digital as this kind of ethereal, sort of immaterial, our lives are going to be more virtual, yada, yada. And so, in our minds, that's kind of not a material phenomenon, and it very much is, right? So one of the things that I really wanted to be sure to include here is a paper, again, that came out just after sort of the first year of COVID, where they're sort of tracking the greenhouse effects of COVID. And one of the things that they found was, look, if you just switch from high definition streaming video to standard definition, right, you're going to seriously reduce the carbon footprint that you cause, right, by streaming all that stuff, right? Another thing we can do, and I can imagine all the videos going off, please don't everyone do that, is turning your video off during Zoom meetings, right? Also, a significant way of reducing your personal footprint, right? Okay, so there are greenhouse gas emissions attached. This stuff is growing. So again, estimates really vary here. And if there's one thing economists love to do, it's kind of, crap all over each other's estimates. So I don't take the absolute numbers seriously, other than they're big and they're growing, seems to be the consensus. This number sort of puts the growth up to from, these guys were at the low end of global greenhouse gas emissions. And they're seeing it move up to about 14% of the world's emissions, right, as things digitize more and more. And there are some key drivers that are sort of well known for why this stuff is really growing. One has to do with cryptocurrencies, sort of very well known, massive energy hog. Another has to do with artificial intelligence. And so the thing that's really gotten attention in artificial intelligence is very large models, particularly language models. So here's sort of a list of them here from a very well-known paper that came out, I think I'm going to say a year ago, 2 years ago. And more recently, Microsoft announced that they trained a model on 32 trillion parameters. Now, what I suspect the authors of the Stochastic Parrots paper, which is the thing you're seeing in the middle there, might say is there's very little actual semantic meaning in 32 trillion parameters, right? So what we're getting out of this is not necessarily clear, but it's big, and there are real questions now circulating about it, when is big too big, right? It's also the case that there's a kind of a social life to where energy comes from, right? So if you're in the data center, you've got concentrated environmental costs, right? You can sort of see it in the water draw, the electricity draw in a very, very localized area. You can see it in the bill, right? So data center managers are very concerned about their electricity bills because it's absolutely massive. And so these things do not go uncontrolled, right? People are really paying attention. For the rest of it, right, you have these very large but very distributed interoperating systems. And so having energy and therefore greenhouse gas emissions be anybody's particular responsibility is a lot harder to come by because things are sort of, peanut buttered around, right? So what that means is that there are real environmental consequences to that social dynamic, right? So in data centers, what we see is much more effort being made for decarbonization, right? So things like putting in renewables on site, brokering deals with utilities concerning green energy, those types of things. There is lots of activity in offsets from an environmental perspective. The environmental advocates will tell you that offsets are not necessarily particularly effective, but that's happening. Once you get into these other areas, well, things are much more distributed. You don't necessarily have as much control over the kind of energy you're getting. And so what you end up with is whatever the national grid happens to be delivering, or the regional grid, if you're in a large country like we are now. And it's also the case that those, the components of those systems are not, the energy draw is not necessarily well characterized, right? So if you're in the data center, you really know every single piece of equipment, how much energy it's pulling in for whatever unit of performance, right? However you want to think about that, right? So, you could build, and there are attempts to do this now, happily, right? You can build on the production side, a carbon neutral PC, right? I'm trying to get to carbon neutrality in its production, and you plug it into the wrong wall and you've still got carbon. Okay, so the thing I'm going to talk about, this carbon responsive computing stuff, is really about decarbonizing what gets consumed. It's not about the other side of the equation that also has to happen, which is just consuming less, period, right? So I hope to convince you later that I think there's an element of this that sort of creates a context in which consumption can also be reined in, but that's fundamentally not what's happening. And so I just want to be very clear about that because, right, it is as important to sort of rein in the consumption side. Otherwise, we're in some kind of fantasy land. But this is the side that we're focusing on. Okay, so what am I talking about here? So one interesting aspect of renewables is that they're intermittent, right? So the sun sometimes shines, sometimes doesn't. In the Pacific Northwest, in November, you're not going to be so lucky. Although today it looks like there's a little bit sort of peeking out. It's not clear necessarily when the wind blows. And so, right, so from a grid perspective, that's a real problem, right? Because you'll have these bursts of energy being generated and then it'll shut down. Same thing with hydro, right? So certain times of year, right, the spring snowpack melts, you get a lot more energy running through hydro systems, and there's excess, and you got to take care of that. So this is a map that I love going to. So if you happen to be a map nerd like I am, and you really have no problem sort of like wasting a good 2 hours of your life, I highly recommend going on electricitymap.org. And what it'll show you is the carbon intensity for any given grid for that hour. Right. So you can't just say, oh, the US has, this mix and France has that. But it changes, right? Because you have these sort of weather dependencies, right? And you have an infrastructure, right? So for example, the Nordic countries have invested very highly in renewables. France has invested in nuclear, which, here is being coded as low carbon. That is something that can be contested, right? So what counts as low carbon is always contestable, right? Here the decision has been made to call it green, right? And Poland has a sort of a long history of coal, right? And so we're not surprised to see that on this particular day, right? Poland is sort of very high carbon intensity. And you can also see wind patterns, right? So later in the talk, I'll talk about a remote island in Scotland called Orkney, and then that's way, way, way at the top. And immediately you can sort of see why they are known for sort of producing massive amounts of wind, right? Because they're sort of like at that point in the jet stream. They also do a lot of marine sort of wave capture, which doesn't show up on this, but also can get interesting quickly, right? So you've got this intermittency, and that's a real problem for the grid. Is less of a problem for computing, as it turns out. One of the techniques, which I think Google is really the first to sort of talk publicly about this, is timing when you run your workloads, right, to sort of meet when there's an excess of or a presence of renewable energy. Excuse me. So Google, again, is the first to do this and to put it into production, as far as I know. There could be other companies who have done it quietly, but Google announced. It's also important to remember that it's not like they just invented it. There is about, sort of a decade's worth of computer science research that sort of, talks about how, the right algorithms that you're going to need to be able to pull this off, right? So, but it is certainly movement, and it's not just Google that's doing it. I can't, obviously, because I don't have visibility into every single large company. I can't tell you exactly who's doing it, but what I can say is that it's the kind of thing that is becoming sort of thinkable in a standard way. So my example of this is I spent the bulk of the pandemic in the south of New Zealand, where I ended up getting stranded. This is a piece out of the local paper, right? This is as local yokel, this is like the Willy Week of Southern New Zealand. And even there, right, so there's all this talk about putting in new data centers. And even there, they're talking about this technique, which they call flexible demand in the context of this, right? So this is the sort of in the same breath as, sea lion shows up on soccer field, right? Like that is literally the other article, that not exactly the same time, but might as well be, right? That's the editorial stance here, right? So it's a cutting edge, but production and common thing to sort of seek to put into production. Okay, so you can also do this spatially, right? And so this is again from Google, where they sort of, what they do is they ship workloads around to data centers around the world where the renewables are present, right? So you can make the same shift in spatial terms. And those are all really wise things to do. What I want to do is be very clear about what the limitations are, right? So, not all computing workloads are time shiftable and space shiftable. And as a matter of fact, that's sort of like a really, I think, important area of research to try to sort of comprehend. The other limitation, and there are sort of a ton of even nerdier engineering limitations that those of you who are inclined that way can sort of dig into. Another one is, shipping workloads to places that are sunny, which is good, but also really hot is a bad idea, because if half of your energy draw comes from cooling the place, then overloading that system even more, right, is not actually going to help things. It turns out that the energy mix that you have, how much solar, how much wind, how much hydro really matters in this. Where one study sort of suggested that actually to pull off geographic load balancing, which is that shipping things around the world, following the renewables is another phrase. Right, there's some suggestion that actually we need significantly more wind to do this, so you just can't rely on solar. And then the last two, are sort of even more serious, right? This does not affect doing carbon responsive computing, doesn't do anything to mitigate the water impacts, which are very serious. So if you've been following the news lately, Google just recently expanded its data centers in the Dalles, or has asked for permission to do so. And one of the areas of serious concern is water, right, which has not been disclosed, and there are freedom of information requests to try to make that public in a context where just down the road in Cascade Locks, right, there's been really significant contestation leading to a ballot measure around sort of Nestle extracting water, right? Where, there are threats of, in the summertime, real drought, right? So this is not going to solve that problem, right? And it's also not going to solve the problem of what's recently being called energy gentrification, which is the social dynamic where large entities like data center owners in effect sort of capture the imagination of local policymakers, local utilities providers, and we find ourselves in a dynamic where those very large, well-paying customers have a bigger say over what's going to happen with electricity, and their needs get prioritized over the people who have been there a long time, right? So not dissimilar to gentrification at all. Right. So again, we're not going to solve those problems. But when you're talking about thousands and thousands of terabytes, or sorry, of terawatts to muddle things, it still matters, and it's still important to do, right? If you can decarbonize it, we should. And so the question that we really ask in the paper is, well, the data center work is good, and it needs to continue, but what about the other 64% of energy, right? So this sort of takes the 2030 projections I showed you earlier and, sort of clarifies the ratio, right? So data center is certainly the largest piece of the puzzle, but not the majority. It's also the case that this is really changing very fast since that graph was built, right? So edge systems, right, which are collections of computing resources, whether that's sort of very small data center, like sort of what's called edge data centers, sort of very small servers, Internet of Things, sort of lots and lots of cameras, or, whatever sensing system you want, right? All of that needs power, right? So there's tons and tons and tons of growth at the edge right now. And so these categories of sort of center and, consumer device don't necessarily hold with that level of growth, right? So what's outside the data center is something that, if anything, we need to be paying even more attention to. Okay, so what we've said in the paper is we said, look, you can call this what you want. There's, I've already alluded to a couple of them: demand response. The energy people tend to talk about it because that's what it is from their perspective. Geographic load balancing, smart grid integration, time shifting, flexible demand. There's a piece of work in science and technology studies where they call it natural intelligence as opposed to artificial intelligence, right? Being intelligent about the kind of the natural rhythms of the world, which I particularly like. Right, whatever you're calling this, our goal is to say, look, we've got to take this out of the data center specifically and start to apply this to everything, right? So we're defining it as carbon responsive computing means energy sources and computing elements of all kinds. You can fill in the blank for whatever that is, whatever you're interested in, that they start to collaborate with the shared goal of prioritizing the usage of energy with the least carbon intensity. And that can happen regardless of whether the strategy is temporal, spatial, or some combination. Okay. So one of the things we're also seeing, if you jump into other elements of the computer science literature, is you're starting to see some forays into carbon responsive computing. So CRC, carbon responsive computing. We're starting to see prototypes in edge systems, some interesting web design, and I'll throw out some ideas about in networking. But just to sort of flag that, there are a couple of sort of feasibility prototypes type work where edge systems, where people are building edge systems to really make good use of microgrids. So microgrids are ways of producing energy that aren't necessarily going on to kind of the full scale, utility. They might use some of the national or regional grid as a backup, but they're kind of designed to be a little bit more independent and kind of keep the energy local, right? And you can do that. What local means depends on, right, who you are, where you're situated. What these folks have done, so this is an Australian paper, and they've essentially said, look, if you've got an edge system with, IoT, a series of devices, workstations, whatever it is, green energy, brown energy, and some battery capacity, right? Then what you really need to do is to start to profile, how much energy you're really going to need for any given task, profile how much, what the temporality needs to be, is it delay tolerant or not, and sort of orchestrate, right, between these different elements. That's my high level anthropologist version of it. I'm sure it just drove many engineers crazy by doing that. But there we go. Another really interesting foray here is something called Solar Protocol, which is a artifact making and doing project that just came up recently in 4S, which is the Society for the Social Studies of Science, which is my sort of professional association. And what they did was they said they built a website that they host at specific servers around the world. So not big cloud computing, but just, who's willing to host this website on their sort of smaller server. And they load the website onto your computer based on which of those servers has access to solar at the moment, right? So when I took this screenshot, I was sort of pinging Australia. And these are the folks who are sort of talking about what natural intelligence means, and then sort of have really interesting social ideas about what that looks like, right? So one reason I mentioned this is I'm talking about sort of big, gnarly kind of computing systems that cost, God knows how much money. This is something you can actually do much higher in the stack, right? As kind of a software designer, right? So I think it's interesting for that reason. Another issue, which my colleague Eve is a networking person. She's actually responsible for one of the protocols that we're using now to be able to run Zoom. That's kind of what she's known for. And so what she's doing is sort of right now in connectivity standards or networking standards is really advocating for carbon responsive packet routing. So for example, if I am in Sweden and I need to send something to Paris, right? If I'm a network, I can make choices about, well, should it actually be routed through Poland or should it be routed through London? Now, of course, where the trunk cables are sort of really limit this severely, but in places where there are choices, right? They could be available to us in a way that they're actually not today. And so one of the things I think this might afford us the opportunity to do is to start building into computing systems some notion of a kind of an energy envelope, right? A kind of if what you're doing is you're having to say, oh, when is my energy available? How much of it am I going to get, right? Where do I have to be doing this computing? Then all of a sudden you're moving from a world where energy is infinite and I don't care to at least there's some limit, right? And of course we can talk about what that would be, and right, there are notions of what's actually necessary and what's not necessary really come into play here. But right? That's kind of where I think we can start to also not, if not tackle, at least give a place for these sort of bigger problems of consumption. Okay, and I'm very much, I'll be under 40 minutes, I guarantee you, but I'll try to be quick for the next part. So energy infrastructure, you know, we all know about renewables. We have seen loving pictures of wind farms, solar, rooftop solar. You know, one of the things that is very clear is the geography of renewables is not the geography of fossil fuels, right? Right? This is not stuff that is underneath the sand of Saudi Arabia. And so, you know, where the wind blows actually really does matter. And that's going to be different. So Orkney is a really interesting site for the reason that there's just tons and tons and tons of wind. There's been tons of R&D and build out of, it's actually one of the largest producers of renewables in the UK. I mean, it is the largest in the UK and one of the largest across Europe. What's interesting about Orkney, and it gets to the broader social point here, is that when you have a different geography, you start to have different actors. And one of the things that renewables are good at is it does not necessarily need to be in large centralized hands, right? So there are sort of people who sort of say, you know, solar is kind of naturally, you know, local, sort of more distributed, owned by smaller actors. There are perfectly feasible ways you could actually make that not true, right? You could build out massive solar banks in the Australian desert or wherever you want to do it, right? You could centralize that, but it lends itself to decentralization, right? I mean, rooftop solar is a really good example of that, right? So you've got all these actors, right? So the important thing, the interesting thing about Orkney, which comes up, and there's a citation later, but there's a ethnography of Orkney that recently won the Rachel Carson Prize, which is, you know, that's sort of the big prize for a new book in my field. And one of the amazing things about it is Orkney has made all this progress, really, really, really serious progress in a community-owned way, right? So they get Silicon Valley folks knocking on their door on a daily basis, and they're very clear that this is stuff that needs to be community controlled. And they do certain things with it to make sure that people on the island are taken care of, right? So the ownership question starts to get really interesting, and the dynamics get a little bit different. So, okay, all right, so we've got computing sort of changing, becoming more carbon responsive. We've got growth at the edge. We've got all these renewables, and oh wow, you can start to do cool things with that. So, you know, when we look across this literature, what we see is new ways of coupling energy and compute. And when you do that, the center starts to look a little bit like the edge, and the edge starts to look a little bit like the center, right? So we saw papers about sort of containerizing, you know, a large, what's called a hyperscale data center, the largest data centers, and siting them next to wind turbines, right? They call this free cooling, which is a really sort of spectacular way of demonstrating just how far away from the natural rhythms, right? The industry's actually gotten to call air free cooling, right? It's a bit ridiculous. To another kind of interesting paper about, you know, sort of doing a proof of concept where they said, look, you can actually take data center workloads and distribute them to people with solar rooftops. So, right, so when they have excess solar, right, they run the compute, get a little money from the data center, everybody's happy, right? There's also at the edge this notion, so there's this notion of public rights of way, which my co-author Eve would be able to tell you about much more than I can. But, you know, this notion of, you know, if mobile phone towers, for example, have solar, right, you can start to ask questions about, well, what do you do when there's excess solar, right? Can you actually start to do some compute, put a shared resource in there that might serve a community? Campuses, right? So this is a picture I grabbed from the internet from PSU, right? Campuses tend to have, you know, some on-site renewables, also typically some kind of on-site data center, although things are moving to cloud, but not everything, right? Because there are privacy reasons, there's latency reasons, there are all sorts of reasons why you don't want to ship everything to the cloud. And so, the question there is, right, what's the algorithm that you need to kind of map the two, right, to make sure that you're optimally using that energy, right? So what I'm really pointing out here is that if we're going to take renewables seriously, then really what we've got to do is have a deeper rethink of where and when computing happens. And I think those examples were the start of that rethink that I think can happen in a much more robust way. Another way of thinking about it, again, coming out of science and technology studies, is as a moment in a much broader, large scale infrastructure change. So Thomas Hughes is a historian of electrical power, and he's sort of written this now classic tome almost about, how is it that we go from sort of discrete invention, right, the light bulb or whatever it is, to a kind of a large scale ubiquitous system. And so he has a kind of a model that of how that works. It sort of looks like a maturity model, but it's a little bit more sophisticated than what you typically find in the tech industry. In that, he's not saying that there's one sort of invention, right, but actually several that sort of come together to make a full system. And then, the kind of the central concept or the ethos of that system sort of moves around different sites, different locations, different countries, and in that moving, right, adapts and changes. So you never sort of stop innovating, right? And then it sort of starts to grow, and you get path dependency and all the rest of it. So what I think is happening, given that we're seeing techniques that started life in the data center out into the world in all sorts of new and interesting ways, right? We're starting to move past that early sort of development kind of moment and starting to move into something you could call maybe technology transfer into other technical areas, not necessarily other countries, because life is global now. Okay, so I'm going to wrap up now by really talking about the social, right, and the social questions that this potential infrastructure change raises, right? So I want to do it by contrasting what the world might look like if you're in a large company like Google. And here I just want to be very clear because I am in no way picking on Google as the only example, right? Lots and lots and lots of big companies, including the one I work for, absolutely see like a large high modernist machine, right? So this is whatever I'm going to say here holds for all large tech companies, right? So I want to contrast that way of thinking, again, going back to Orkney, right? What does the world look like if you're on Orkney, right? And when you're in a big company, right, the world looks flat, right? Right, the world looks as if Thomas Friedman sort of describes it, right? Where you own data centers all around the world. So of course you can just ship it off, right? It's seamless. It's those are no cost. You don't have to knock on somebody's door, right? It's there, it's yours, right? The world is flat. If you're in Orkney and you've built this massive community-owned renewable energy infrastructure, right? Life is a little different, right? What you're going to build is you're going to look for partners to exchange with, right? You're not going to assume that you sort of own everything, right? You're going to want to figure out, okay, when the wind is blowing, whose workloads can I take on, right? When the sun is shining down in Spain, and our wind is nothing today, right? Where do we send ours? And so you're going to build a whole system of exchange, which requires a bunch of technology. You're going to do that in a different way. Another way this manifests is in those maps I was showing you earlier with the different energy, right? So those are energy measurements taken from a national grid. If what you have is an on-site renewable, even if there's coal all around you, it might still make sense to send data there, right? But you can't necessarily, if microgrids are not important because we're only dealing with national grids and very large companies, right? will never have the opportunity to do that, right? So all these different social systems and technical systems need to start working together in equitable ways, right? And we need to be very clear about what that is, right? So here we've developed this kind of framework for the kinds of the dependencies and between different elements, right? So in the center is carbon responsive computing, right? So that's questions about both engineering and social questions about action, right? What can you do? How time sensitive is this? Where can you send the workload, right? All of those types of questions, but also the social questions, right? To whom can you send that workload? Who can borrow your energy, right? All of those types of things have to be asked too, right? On the carbon aware side, right? The part of the glue that holds us together is data about carbon intensity, right? And so again, we start to ask social questions, right? Who's at the table to define what counts as low carbon and high, right? Is the nuclear industry at the table? Right? Like those are the kinds of things that need to be asked, right? For folks who own microgrids, like how much of a role should they play in that? And should their data be treated differently, right? Should aggregation actually be centered around very large players or very small players? I mean, then finally, right, you have like, okay, what are the implications of all of these actions, right? So, and for example, if more and more carbon responsive computing starts to happen, right? So you've got data centers all down the West Coast, right? Or edge systems all down the West Coast, whatever it is, they start to sort of delay, right? Workloads that sort of pile up over time. And then all of a sudden the sun starts shining. Ooh, okay, now it's going to ship out. And if you are a networking person, then you have a problem because you have a large burst of workload, many packets you've got to deal with all at once. You might have to change how you do networking, right? You might need to change how many batteries exist for, what particular site, right? There are all sorts of follow-on infrastructure questions that arise once we start thinking in these ways. So these are the things I've talked about. I talked about the scope of the problem, the changes in both computing and energy that are happening, how those things can come together, and these social questions. And I just want to leave with a real sense of urgency, right? That this is something that really needs to happen sharp. And it reminds me of the old proverb that the best time to plant a tree is 20 years ago. The second best time is now. So I'll stop.